Welcome to the next video in the course in real analysis. This is lesson 2, discussing rings and fields. Before we go on, I'll give a quick summary of the things that you'll find in this video. So we have a definition of a commutative group, the definition of one operation distributing over another operation, the definition of a ring and field, examples and non-examples of rings and fields, and then exercises at the end. So as before, the point of doing what we're doing here, defining all of these things so that ultimately, eventually we can define what a ring is in the first place, in order to use this definition to then state an axiom for the real numbers, right? So all of this is in service of stating axioms of the real numbers. So once we know what a ring is, and in fact, not even really just a ring, but a field, but field comes after ring. So in any case, it'll be an axiom that the real numbers form a field, but we have to say what a ring is first. But before getting to any of that, let's start with the definition of a commutative group. So we're going back to the concept of a group, and we'll say what it means for a group to be commutative. Well, all it really means is just that the operation associated with the group is commutative. And the definition of an operation being commutative should be familiar from a discrete math class. Okay, one other prerequisite definition that we're going to need is the idea of distribution. So let's set R to be a non-empty set. Okay, it's just a set. Who knows what its elements are? And this time it will have two operations. Now they could be any operations because again, this is abstract. We don't know what R is, so we couldn't necessarily know what plus and times are. I'm just telling you that there are some two operations. And again, recall, maybe I'll even write it out just to make sure that this is fresh. So recall that what it means for these to be operations is that plus has as its domain R cross R. That cross symbol maybe at the moment is a little inconvenient because it might get a little bit confused with this the symbol for the operation itself. So I hope that doesn't cause too much confusion. But anyway, so saying that plus is an operation means that its domain is the Cartesian product of R with itself, and its range is R. And also X, which maybe I'll write kind of big. That's the operation X is also an operation, and being an operation means that it has domain R cross R over to R, the small cross being the Cartesian product. So hopefully that's not too ambiguous. That usually doesn't cause a problem, so I'm not going to worry too much about that slight ambiguity. But that's what I mean when I say that these are two operations on the same set. Now, we will say that multiplication distributes over addition, right? We'll just talk about the cross symbol being the symbol for multiplication, even though in the abstract setting, we don't really know what it is, but we're just going to write these evocatively as if they were plus and times, even though this is currently abstract. But anyway, so we will say that the times operation distributes over the plus operation if for every choice of 3 elements from R, call the choice of 3 elements from R, A, B, C, then when you write A times B plus C in parens, then you get the familiar distribution of A into the sum, and likewise the distribution also holds when distributing from right to left into the parentheses. And okay, now having established the meanings of all of these terms, we're in a position to define what a ring is. So again, we're going to say that R is our non-empty set. It again has 2 operations, kind of the idea of a ring is moving from group to ring. Group is all about a set with 1 operation. A ring is all about a set with 2 operations that interact. And so we say that this set R, together with its plus and times operation in that order, right? The plus and times will have different restrictions, so it's important to distinguish which ones we're imposing these conditions on. So, okay, let's give the conditions for this thing, R together with plus and times, to be a ring. And with all of the definitions, as we have established them so far, now make it relatively straightforward to state what a ring is. So to begin with, let us restrict our attention to the plus operation. That must form a commutative group, right? So we now know what a commutative group is, and when this well, this is a condition for being a ring, is that if you just consider the set with only the plus operation, that forms a commutative group. We will now traditionally write the identity element, even in the abstract case, with the symbol 0, evocative of the number 0. And then we also require that times is associative. Okay, well, plus is associative because that just came for free when we said that R together with plus is a commutative group, because being a group, one of the conditions for that is that plus is associative. Well, we're not going to say the same thing for the times operation. The reasons for that, maybe they will kind of come out as we go through the rest of this, but we're not going to say that it's a group with the times operation, but we do still want the times operation to be associative, and we want it to have an identity. We will write the identity element with the numeral 1, again, evocative of the number 1, even in the abstract case. And finally, we will require that multiplication distributes over addition. So this, right, this collection of properties are all things that are familiar to the, various number sets, from the integers to the rationals, reals, complex numbers, and so on. But because it is more abstracted, there are some things which are rings, which are not numbers. But we'll see those examples in a minute. Let's just say a few more words about what we have here. So as I already mentioned, we're using the plus and times operation evocative of the numbers, even in the abstract case. We'll generally use plus notation for all kinds of things whenever we're talking about rings and the plus operation. So for example, when we were talking about groups, we typically used multiplication notation just as a default, even in the abstract setting. And so to write the inverse of an element for a group, we would write it with the superscript -1. We're not going to do that when we're talking about a ring. Instead, we'll use the -x, right? That's the notation that is evocative of how plus is typically written. And so when we're talking about a ring and we're using the plus operation in the ring, right, when we want to talk about the additive inverse element for a given x, then we'll write it as -x. Now, when we're talking about, inverse elements for multiplication, we'll use multiplicative notation, right? That's where we'll use the superscript -1, is when we're talking about the inverse of an element x for multiplication. And it's probably worth emphasizing right now that not every element of a ring has to have an inverse multiplicative inverse. And even if you think about familiar number examples, not every element of a number set has a multiplicative inverse. And that is because of the number 0, typically, for most number systems, well, really every number system that comes to mind at the moment. So, okay, let's move on to looking at those examples and non-examples of rings. So one of the most basic and important examples of a ring is the set of integers, with plus being the normal, usual plus operation. So when I write plus here, that's what we write when we're being abstract, but in this particular case, that's also what we write when we're talking about integer addition. So this, I now mean the integer addition. So, and likewise for the multiplication operation, when I write the times here for this particular application, I mean the usual integer multiplication. And now, as an example of something that is not just straightforwardly numbers, right? Matrices are not numbers. Okay, they're often not always, but often grids of numbers, but they're not numbers. And so that makes this a non-numeric example of a ring, right? I claim that if you take the, say, real n by n matrices, it doesn't have to be real, it could be integer matrices, it could be rational number matrices and a bunch of other things, but let's just talk about the real n by n matrices. So that's our set, by the way, right? Important to distinguish what is the set of elements before talking about the operation. So here the set of elements, right? Each element is a matrix. And then we'll talk about the plus operation, where this time the plus operation is the addition of matrices. And we'll have a times operation, which will be the multiplication of n by n matrices. And I claim that this is a ring. Why is it a ring? Well, I claim that when you focus on this with only the plus operation, you get a commutative group. And that fundamentally, we've already seen that it's a group. Why is it a commutative group? Well, things swap around the plus operation, and you can prove it because, like if you did like a coordinate-wise calculation like we did in a previous exercise, it's pretty straightforward to demonstrate that the plus operation commutes. So when you think of the set with the plus operation, you have a commutative group. And then the multiplication operation. Well, is it associative? Yes. Famously, matrix multiplication is associative. And does it have an identity? Yes, that's the identity matrix. Notice that this is kind of where it's important that we did not say that the multiplication operation forms a group, because if we said that, then matrices would not be an example of a ring. Why is that? Pause the video, think about it, try to come up with your own example. But I'm gonna now assume that you've already paused and thought about it and want to compare your answer to mine. Why, if if we're talking about this example of n by n matrices, and if we had said that the multiplication, the set with multiplication is a group, why would that not be true for this example? Well, it lacks inverses, right? Not every element has an inverse. The zero matrix has no inverse, but also other matrices, like here, let me just go ahead and write a matrix with no inverse. So 1, 0, 0, 0 is a 2 by 2 example of a non-zero matrix with no inverse. So anyway, just one element with no inverse would be good enough, but I figured just for good measure, I'd show you another. So anyway, there you have it. So precisely because the definition of a ring does not require that the multiplication operation form a group, then matrices, or n by n matrices like we have here, forms an example of a ring. Okay, and let's now look at a next example. Oh, sorry, yes, oh, right. And there's one more thing to check when you're thinking about whether or not an example is an example of a ring, and that is distributivity. But yes, right, this is a famous thing to check in, say, a linear algebra class, which is that matrix multiplication distributes over matrix addition. You can check it coordinate-wise if you wanted to, but I won't do that now. So anyway, let's talk about one more example, and let's consider, this will be a non-example. So consider the set of vectors in, just for specificity's sake, let's talk about R3. And let's have a plus operation. We all know of a famous and perfectly good example plus operation for vectors, right? It's just coordinate-wise, it's basically matrix addition, right? So there we have a plus operation. What about a multiplication operation on vectors? Especially in R3, we have two candidates that probably come to mind, and that would be the dot product and the cross product. If you haven't had multivariable calculus, then you may not know what those are, but they're fairly straightforward. I wouldn't necessarily say that you need to go and study multivariable calculus before studying real analysis, because this is just an example. But basically, if you had, should I go over it? Should I say what it is? If you're not familiar with the example, don't worry about it too much. Just know that there are these two operations. They kind of behave like multiplication for vectors. in 3 dimensions, but they don't satisfy the axioms of being a ring. And so for those of you who are familiar with this, why does the dot product not satisfy the conditions for being a ring? Well, because the dot product is not even an operation. Think about it. You take 2 vectors in R3, you dot them together. What do you get? You get a real number, not a vector in R3. So it's not even an operation. So certainly we couldn't use that to make an example of a ring, right? So we've got a set, we've got a plus operation. Those are good. It's even a commutative plus operation, but the dot product does not serve to make this into a ring. What about another multiplication operation for those of you who are familiar with it, the cross product? Well, that is an operation, right? You take 2 vectors in R3, you cross them, you get another vector in R3. So sounds good, at least it's an operation. But then what about the various properties? Well, this operation is not even associative, and you can demonstrate it for yourself if you care to, but all of this is basically just to demonstrate that this also does not make for a ring, right? So with the plus operation and the cross product as the times operation, you don't get a ring. These are non-examples of rings. And finally, for good measure, let's see another non-example. And this time what I kind of want to do, I'm trying to come up with an example where I violate the axiom or the condition that this thing should be a commutative group under the plus operation. Is there any example where, you know, we don't even have that? And so, yes, in fact, maybe I can reuse one thing that we've talked about before, which is the group, right? So it is a group. That's also one thing I was kind of hunting for, something that is a group. It's just not a commutative group. So remember, when talking about groups, we talked about the set of all functions, the space of functions, which were bijections from x to x. And we showed that that was a group. Well, I claim that it is not a commutative group. And so what all of this shows is that if you took that as your set, in the language of rings, we would set that equal to R, right? And then if you tried to make the plus operation, the operation that we used in this example, which recall was the operation of function composition, then this would not form a commutative group. And so you would never get a ring by doing anything like this, basically. Or at least so long as the cardinality of the set is strictly greater than 2. If it were not, that would be a pretty boring and trivial example. So so in any way that is interesting, you'll never get a ring formed from the set, the set of bijections with the operation of composition. Okay. Having introduced all of that stuff, let's now move on to the concept of a field, which is, in a sense, kind of what we're more interested in. As a prerequisite definition, just like with groups, we say that a ring is a commutative ring if the times operation is commutative. So it's kind of similar to what we said about groups, right? Because we were talking about like the entire group, the whole structure of the group is a commutative group if the operation is commutative. Well, here, when it comes to rings, when we say a similar thing, we already have that the plus operation is a commutative operation, because that's just part of what it is to be a ring. So we don't need to say that, but you know, since the multiplication operation might not be commutative, and by the way, probably now's a good time to note when it comes to matrix multiplication, that's not a commutative ring because matrix multiplication is not commutative. But when the multiplication operation does commute, like say with the integers or lots of other number sets, then we say that the ring is commutative. But okay, with this sort of prerequisite definition having been established, we can now say what it is to be a field. So now let's say that F is our non-empty set with the plus operation and times operation on F. We say that this, and actually what I probably should say is, although it is common to talk about F is a field if blah, 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 really it's in a somewhat more technical sense, although we don't often stay this technical, but if I want to really be technical when I first introduce the definition, then this is the thing that we would actually be calling a field. It is the triple of the set F together with the plus operation and the times operation. So we say that this thing is a field if it meets the following conditions, which is that it forms a commutative ring, and that ring must have an addition, additive identity 0 and multiplicative identity 1, where 0 is not equal to 1, which seems like a funny thing to have to say, but if you go back and check the definition of a ring, nothing in what we said about a ring forbids a ring to have only a single element. And in fact, I think I made this actually one of the exercises at the end of this video, so you'll see more about this idea later. But anyway, long story short, we do technically have to state, if we want this, we have to state it because it doesn't come for free from the earlier parts of our definitions. So we enforce that if anything's going to be a field, it must have a distinct, different additive and multiplicative identities. Okay, so that's part of the condition for being a field, to be a commutative ring with a different additive identity from its multiplicative identity. And then moreover, to be a field, the times operation must have inverses for every element other than the additive identity 0. So that is to say, if you take any element other than 0 from your set, then its inverse must be in the set. So when something meets these conditions, we say that it is a field. Okay. Now, typically when I introduce a concept, I like to give examples and non-examples. Examples here are easy. They're number sets, right? So if you took the integers with plus and times, that would be a field. If you took the rationals with plus and times, if you took the reals, the complex, those are all examples of fields. But this is a pretty restrictive definition. And there just aren't a ton of non-numeric examples of fields. So, matrices, because they lack inverses, then they are not examples of fields for pretty much any example. And so, coming up with examples, coming up with examples other than the number sets is pretty hard. There are some interesting examples, but it typically requires, there's this thing called the field of fractions for any given ring and blah, blah, blah. But you really got to study quite a lot more abstract algebra before you can kind of understand what those things mean. So I won't go into it. And so we'll just it's fine if you mostly think that fields are basically numbers, right? Some kind of number. It could be integers, rationals, reals, complex. In fact, it turns out that certain sets of numbers mod p, right, where p is a prime number, right? There's this notion of arithmetic mod p, and there's a good set of examples of things that can form a field. So anyway, I don't want to go into that in too much detail because it takes us a little bit away from what we're trying to get at. So there you have it. I hope that's a clear enough explanation of what a field is. And so let's get on to the exercises. So to begin with, let's talk about what I was talking about a little while ago, which is to show that just the set of 0, right? Notice that this has only one element. I'm calling it 0, but it's going to be the additive identity. But since there's only a single element in the set, then really there's only a single operation on this set. And so that is in fact part of what you should show, is that there is just one thing that any operation could be, and therefore because it has only a single element, then when we talk about the plus operation and the times operation, there's only one thing I could possibly mean for both of those, and it'll be the same thing. But anyway, once you have all of that, show that what results, right, the set, which is just the set of 0, the set of this one number or element, if we want to treat it abstractly, together with the operations, and there's only one thing that the operations could be. Once you have those components, the result technically is a field. It's a boring field, right? There's not much to say, or sorry, I said field, it's a ring. It's a boring ring, there's not much to say about it, but it does technically meet the conditions that we gave for being a ring. Okay, for problem number 2, suppose that you have any group, and you are to show that in any group, the identity element is always unique. Now, to say a bit about how you approach a problem like that, in general, in any mathematical setting, when we talk about something being unique, somewhat formally what that looks like is that if you assume any other element has the same property, here we're talking about some other element, I've written it as x here, has the property that defines an identity element, namely that if you take x, product that, or whatever, with any element y from the group, and you get y, and it's the same thing if you did it the other way around, right? That's the property that defines what an identity element is. Well, in theory, right, there's, for any given property, there's no reason to assume that only one element enjoys this property. We know that E does because that's an axiom of the group, but might there be this other element X that also enjoys the same property? Well, what you are to do is to show that no, in fact, whenever anything, right, if X is anything and it has this property, then X must equal E. That's how you show, that's how you show that the property, or that the identity element is unique, that it is enjoyed by precisely one element. And then what I'd like to do is have you show that in a ring, right? So you show that the identity element for both the addition operation and the times operation are unique in a ring, in particular, leveraging what you just showed in exercise 2. Now, for the plus part, that should be extremely straightforward, but for the times part, it's not so straightforward because we don't know that the set together with the times operation is in fact a group, and so you can't just merely appeal to a result that talks about groups. But what you can do is simply retrace the proof, and notice that the proof does not use any facts about inverses. I promise it won't. So there's a guide or a hint for how you can approach this problem. So, okay, for problem number 4, we're going to prove that 0 times anything is equal to 0. Seems like a fundamental fact that perhaps you've never even doubted, but here we'll give its proof from the axioms. And just to give a hint for problem number 4, let's think about this, right? We're talking about 0 times any number. That's a multiplication fact. But 0 is the additive identity. So this has to have something to do with the interaction between addition and multiplication. Well, 0 is special because it's the additive identity. Try to think about how you could use that fact. And also distribution is the fact about how addition and multiplication relate to each other. So try to see how you could use distribution as well for problem number 4. Okay. For problem number 5, again, we're going to prove what sometimes feels like a completely basic fact that perhaps you don't even doubt, which is that the negative of x, right, which is to say minus x, the additive inverse of x, right? Recall, what does that mean? Just to be clear, that means the number which, when you add x, you get 0, right? That's what minus x is. We're going to prove that you get the same thing when you take x and multiply by -1, right? So we're going to prove this identity, that negative x is the same thing as -1 times x. So, before getting into the problem, make sure that you appreciate how each side of this, strictly speaking, expresses something different. And what we're going to prove is that they actually result in the same object due to the axioms. But so again, right, the left-hand side is the additive inverse. The right-hand side is a number times a number, right? Now, to give you a hint about how this goes, essentially what you'd like to do is to show that this thing on the right-hand side has the property that when it is added to x, the result is 0. That'll make it the additive identity. Why does it make this the additive identity? Well, a somewhat subtle but important step there is that we proved that the additive inverses are unique. So we have a proof that if anything has the additive inverse property, it must be the unique additive inverse, which is expressed by this minus x. So when you show that this has the property that when it is added to x, the result is 0, you've shown that it must be this unique element that enjoys that property. So, okay, that's enough of a hint. And finally, use what you've shown here to demonstrate that, oh, I didn't even write what it is. Oops, I didn't write what it is. Sorry, I should have written that -1 times -1 is equal, no surprise, to 1, which notice is not an immediate consequence of this, right? This is saying that you can move the additive in, right? Like if you have something times -1, you can instead rewrite it as the additive inverse. So there's a quick and obvious move that you can do right away. But once you're there, it's not completely granted that the result is 1. So then from that point, right, once you've made that move, then think about how in any group, the inverse of the inverse is the original element, which is an easy thing to prove. You will need to prove it, but it's very, very easy and direct. So there are your marching orders. And so you'll see my solutions in the next video. And as always, I'd like to close each video with an invitation to ask questions. So if there's anything in the textbook related to this, although exactly where you would be looking in the textbook, I'm not sure. It does talk about rings and fields, but I haven't assigned that as reading. But if there are pretty closely aligned sections of the textbook and you have any questions, leave a comment. I might be able to answer that in the comments. And if it's a substantial enough and interesting enough thing that I feel like I have time to make another video dedicated to answering that question, then I might do that and insert it in the playlist.